This is an example of hypothesis testing with a correlation coefficient. So we have 30 observations of the masses of two reactants in an experiment. The scientist calculates a product moment collision coefficient and gets minus 0.45. Now, of course, that is negative correlation, and we'd maybe describe it as being moderately strong. The scientist believes there is no correlation between the masses of the two reactants. Test at the 10% level of significance, the scientists claim, stating a hypothesis clearly. So this question really says, is a correlation coefficient of minus 0.45 strong enough for a sample size of 30 observations to come to the conclusion that these two reactants have a negative correlation, or in this case, any correlation at all. Of course, this is just a sample of 30 observations, a sample from a population. So our hypotheses here in this type of question always begin with a null hypothesis that the population correlation is zero, or there is no correlation for the whole population. Now this symbol here is the Greek letter rho, R-H-O, rho, and it represents the correlation coefficient for the whole population, whereas R represents the correlation coefficient just for the sample. So scientists believe there's no correlation. That is our null hypothesis. Make sure you do not use R here. You must use rho. Our alternative, we're testing the claim. They believe there's no correlation, so we're testing that claim. So our alternative is that there is some correlation. It could be positive, could be negative. So it's rho does not equal zero is our alternative. That makes this a two-tailed test. And since we were told to use a 10% level of significance, that means 5% in each tail. Now, a few moments ago, I mentioned that this value of R, minus 0.45, we now need to decide, is that strong enough for us to conclude that the population correlation is, well, or there is any. In your formula book, there will be a table of values with product moment collision at the top. We need to now find the critical value from the tables. You don't need to understand how these have been calculated, but these give us the cutoff values to decide whether minus 0.45 is strong enough or whether it isn't. If it's not strong enough, then we're going to keep the null hypothesis. However, if this is strong enough, we will then reject the null hypothesis in favor of the alternative. So along the top, we need to look at the level, 10%, 5%, 2.5%, 1%, or 0.5%. Originally it was 10%, but then it was a two-tailed test, so 5% in each tail. So actually going to look down the 5% column. And the sample size, 30 observations, sample size 30. So down the 5% column and across the 30 row gives us our critical value. So from the table, the critical value or values are plus or minus 0.3061. I put plus or minus because it is a two-tailed test. So if the correlation had been stronger than either positive 0.3061, so if R had been positive and it had been stronger than 0.3061, then we would reject the null. Alternatively, if it turned out to be negative, which we can see it did here, we need it to be smaller than minus 0.3061 to be strong enough to reject the null. If you get your head around that bit, these are the values which tell us how strong the correlation needs to be, and if it's stronger than that, then we reject the null hypothesis and conclude that there is some correlation. So in this particular case, our R value is minus 0.45, which would be in this rejection region here. So yep, we will be rejected in null. Minus 0.45 from a sample of 30 is strong enough evidence of a correlation between these two variables. So that sentence there is just describing what my little diagram was saying. So since R is minus 0.45 and it is less than minus 0.3061, we will reject the null hypothesis and conclude that there is sufficient evidence, so there is enough evidence at the 10% level to suggest a correlation exists between the masses of the two reactants.